Welcome back. So, in the previous lecture we were talking about the importance of the folds and putting the dam structures here. Now, let us see very quickly the faults. We have discussed quite a bit about the fault and its importance, that why we should know the fault planes and all that, or the fault lines on the surface. Now, this is an example of the shear zone which we located close to again Chandigarh. This is what you will find, okay, in the shear zone. So, you will have the very shattered rock in the shear zone because of the deformation, and this will result into the extreme problems when you are putting structure on this, okay, because they do not have good shear strength along that, and if there is a movement on this, then you will have problems on the structure sitting right on the top of that, okay. So, this is another example which shows the shear zone. Here you can see the shear zone. Now, what we did here was that we have the young deposits which we call the quaternary deposits in terms of the period. So, these are very young deposits which are sitting on the top, and this young deposits are also displaced, okay. So, this is another example of the sectional view of the strike slip fault here, okay. So, we have a bedrock here. This is the level of the bedrock, and here on this side we have the level of the bedrock here, okay. And this is this is what we call we are marking as a fault here, okay. So, there is an displacement where this block has moved down, this has moved up, and so this is a typical strike slip fault which we are looking at, and probably we are having a thrust component in this, okay, where the right hand side has moved up, okay, compared to the left one, okay. So, this is we come across like in terms of if we have to look at the shear zone, okay. So, we need to avoid putting structures on the top of this, okay. Now, coming to the importance here, faulted areas are neither safe nor stable, okay. Faults causes considerable fracturing and shattering of the rocks along the fault zone, okay, which reduces the physical strength, okay. So, shear strength of the rocks goes down, okay. So, these are not good for the foundation, putting foundation or putting buildings, and they are not like very good. And when fractures and faulted zones get saturated with water, so in hilly terrains mostly you will have this seepage of water is going on, and if you are having faulted or fractured zones, they will be most ideal zones for water to pass through, okay. So, that further reduces the shear strength, okay. And then fault acts as channelways for the movement of groundwater and causes leakage problem from the reservoirs, okay. So, this we were talking in terms of the folded areas where we are having fractures and all that, or maybe we are having the bedding planes which are inclined, okay. And most important features of the fault is probability of the recurrence of the displacement on the same place, okay. So, you will have, because we were talking about the recurrence interval, okay. So, the same similar magnitude earthquake may recur on the same fault, okay. So, that means that they are having the potential of displacing the surface in near future and triggering a large magnitude earthquake. Faulting is usually accompanied by earthquakes which causes strong ground motion, okay. So, how far you are sitting from the fault, that is also important, because that will result into the ground shaking, strong ground shaking, okay. So, important to know the history of past earthquake. This is what we are now slowly getting into the this mode, where this type of studies will be extremely important and mandatory, okay, for any structure which is coming up close to the faults, or maybe in the seismically active regions, okay. So, if you look at and go back and look at the seismic zonation map, so at least in 4 and 5 any structure is coming up, we need to have this understanding, okay. So, that means you need to know the history of the past earthquakes, their magnitude and repeat time, that is a recurrence interval, and the sense of movement, amount of displacement during single event. This all information will be required for any upcoming civil structures or the construction in that area. Okay. So, this information will be required by the planners, town planners, to design the building accordingly. Okay. Now, in most of the parts in India, we do not have this information available. Okay. So, still the studies are going on a very large scale. Maybe in couple of years, we will be having very good information on this aspect. Okay. Now, precautions to improve the fault sites. Okay. People have been talking about, and many research groups have done this. Okay. So, what precautions have been taken if you come across the fault zone? So, first of all, it is always desirable to avoid the site where the faulting has occurred, but it is always not possible. Okay. Because you cannot say that, okay, I will not cross this fault. You need to cross the faults in some locations. Okay. Otherwise, the cost of the project will increase, and it may be difficult that you avoid the faults. Okay. You have to cross the faults. So, you need to know that what will be the possible recurrence on that, what will be the amount of displacement on that which is expected, and then what will be the magnitude of earthquake which is expected on that particular fault. Okay. So, what is the sense of movement, etc., you need to know, and accordingly you can like come up with your building plans and all that. Okay. Now, then we need to know the tectonic history of the area should be studied very carefully. Depending upon the magnitude of the past earthquake, the structure should be made or planned in such a way that it can withstand the shaking, or if you are having a flexibility, it can accommodate that displacement also. Okay. Now, if suppose if the faulting has not recurred in the recent past, so there is no earthquake in the recent past, as we were talking about that the Pinchore Garden fault did not experience any earthquake in last 400 to 500 years, but then the likelihood is more on that fault, okay, to trigger a large magnitude earthquake. So, if you are not having any occurrence of any earthquake on this, then the damage caused by the region should be carefully assessed, okay, because it is long time which has been passed since the last earthquake on that area. So, people have very short memory and people will forget, and we will not be able to take into consideration what happened in the past. So, if it is possible, if you are having good historical chronicles, you can try to look at that what type of damage was there during those earthquakes, okay, and accordingly the assessment of the hazards should be done. Okay. Now, some locations, what they do is that they try to grout the fault, okay, and then strengthen that area by injecting some thin slurry of the cement and all that. Okay. So, that to some extent you will be strengthening the faulted area. Okay. You may remove the shattered zone, or you may remove the shattered rocks and the crushed sheared rocks, and then you can refill it by the concrete or something like that to strengthen that part. But my only point is that the fault is not so short, okay. Fault is quite extending for a larger distance, okay, and rupture will not be just in couple of meters, okay. It will cover kilometers. So, how you are going to seal that particular fault, okay. Of course, if you know the history of the fault, and if you know and understand that this there will be no earthquake in future on this fault, however, there is an old dormant fault, is not an active fault, then the shear zone or the shattered material can be removed, and you can do the grouting part. So, that at least we are putting the heavy structure on the fault or the shear zone, it will not allow it to slip, okay, because of the overburden. Otherwise, you may not be able to fix up in a proper sense, okay, if it is active. So, you need to know that what the past activities, okay, past earthquakes, whether it has triggered or not, okay. So, if there is lot of shattering in the area due to past faulting, the whole loose mass should be removed and refilled. Okay. So, if you are having an old fault and then you are doing that, then you can consider that concreting and grounding part. Okay. There is absolutely no problem for that. Now, suppose we have the same part. We let us take, actually we are having a dam here, and then we put we have this is the upstream direction, this is the downstream directions we are having, and we have fault like A dash, okay, and then we are having a fault. So, one fault, in both the cases the faults are away from the main structure, because we in any case we need to safeguard the dam structure. So, for example, both the faults are away and both are dipping in different directions. Okay. So, one for example, if we take this is south and this is north. So, one is dipping towards north and another dipping towards south. Okay. So, both are away from that. Okay. So, fault A is dipping in the upstream direction, okay, and then B dash is dipping in downstream direction, and both are far away from the main structure. So, such faults are not harmful unless the tectonic history, okay, indicates that they are active, because if they are active, then they will trigger a large magnitude earthquake. They will not damage directly, but indirect damage will be there to the structure. And here, then in that case, we have to take into consideration what will be the ground shaking, the intensity of ground shaking at this particular place because of these two faults. Okay. So, that has to be taken into consideration, and again accordingly the structures can be designed. Okay. Now, there is another fault again from the same place, okay, if you are having, but one is dipping. No doubt the surface manifestation, if suppose the geologists take up these studies and then they found that, okay, fine, there is a surface manifestation here of the fault, and then there is another surface manifestation of the fault here. Okay. So, in the initial cases what we were looking at, and that is extremely important, because what we are looking at the attitude of the fault plane, okay, or the fault. One is dipping in away from the in the downstream direction, another is dipping away again in the upstream direction. But these two faults, which is marked in the pink dashed line and the blue dashed line, they are having the same surface manifestation here, but they are dipping in such a way, okay, one is dipping in, for example, in the upstream direction, another is dipping in the downstream direction, okay, and both are crossing the structure somewhere. Okay. So, when there will be a movement will be along this plane, okay, and that will result into the damage to the structure. So, these two faults are okay, but these are not. So, we need to know that in which direction the faults are dipping and what will be the sense of movement on that. So, just saying that, okay, fine, my fault on the surface is not crossing, or the structure is not crossing the fault, that will not be enough. Okay. Where you are setting, okay, where your structure is setting with respect to the attitude of the faults, okay, that is extremely important. Another one is here. So, in this case, okay, this is absolutely not ideal. Okay. So, this is absolutely not ideal. Now, I am just going ahead. I think this we have already discussed. Now, location of the reservoir in case of the faults, so if we take into consideration faults. So, in case of the inclined beds in the upstream direction, this we have talked about in the type of folds. Okay. So, there will not be any leakage from the reservoir if the downstream direction, if you are having the beds which are dipping in the upstream direction. Okay. So, this is one thing which is important. Now, if the leakage, if the beds are inclined in the downstream direction, then you will face the problems with the leakage and all that, and we have discussed that why this site is extremely not important, or not ideal to be put. Okay. And then in case of the horizontal, it may be minimized. Okay. So, in any case, if you are having like folds here like this, okay, what we have talked about, so this may be the ideal one, okay, to put, but this is not at all. Okay. This will result into the slippage and all that. Okay. Now, coming to part of the tunnels where we are taking into consideration, mostly we are crossing the folded limbs or the folded areas. Okay. So, tunnels are underground passages either to route for the your regulatory traffic, or sometime we use to regulate the water also from one reservoir to another one. Okay. So, and then the most important part is why we put tunnel is to reduce the distance, otherwise we will be covering long distance to just to reach across the hill. Okay. So, economic aspect of the tunneling mutually oppose one another. This is what has been found. Okay. Okay, where the tunneling can be expected to be completed very fast, okay, economically, and if lining is not necessary. If such areas are been found, then it is fantastic. Okay. But to some extent it is difficult. Okay. So, economically, if you have to put the tunnel, we have to see that, okay, fine, how fast you will be able to complete that project, how economical it will be in terms of the cost and all that. And so, and if you are coming across the excavation part can be finished very fast, no lining is required inside. So, then that project is fantastic. Okay. But this is possible when we get a very soft rocks. Okay. So, excavation will be very fast and you will be able to do that, or weak rocks, because you will be able to excavate fast. Okay. So, either you come across the shale, you come across the rocks which are weakened because of the fracturing or jointing. Okay. So, those areas you will be able to excavate very fast, but such soft and weak rocks are not capable to withstand the tunneling process, okay, and may result into partial or total collapse of the roof, because you are removing the or removing the strain part on that from that. Okay, and then that can result into the collapse because of the already the rocks are fractured. Okay. So, that can be one of the problems, and then you will have the seepage problem also. Further tunneling in such situation may lead into severe groundwater water problems. Okay. Okay. To avoid this, lining has to be done, okay, which is again will be very expensive. So, you want to do the project in a very quicker sense, but at the same time, because you are excavating in the softer rocks, you may face this problems. Okay. So, you may have the collapse problems, you may have the water seepage problem a lot. Okay. And that will end up in having more cost of the project, because you have to put the lining and all that. Okay. On the other hand, excavation in the hard rock, okay, because you want to avoid the collapse, you want to avoid the water seepage and all that. Okay. For example, if you are coming across a massive granite or competent formations, okay, tunneling will be extremely slow and cost wise it will be expensive. Okay. But the tunnels through such formation will be safe and stable, and hence do not require any lining. Okay. So, you can try to look at such, but it will be time consuming and expensive, but it will be safer. Okay. Now, tunneling in igneous rocks, especially in softer ones, so like for example, we are having vesicular amygdaloidal basalts are competent and suitable for tunneling. Okay. So, we will see a couple of examples here now. Now, this what happened in tunneling in Talghat on the Bombay Delhi railway line, okay, and Bhorghat on the Bombay Pune line were excavated through amygdaloidal basalt without any problem. Tunneling through sedimentary rocks, thick bedding, well cemented siliceous or ferruginous sandstone are more competent and better for tunneling. Okay. Whereas argillaceous sandstones, okay, fine grained sandstones, or you are having shale and all that, that will be weak and undesirable. Okay. So, this is what one should keep into mind. So, whatever you have learned in the previous one, all you are applying here actually. Okay. So, you are talking in terms of the bedrocks, what type of rocks you are coming across, whether they are sedimentary, metamorphic or igneous, whether they are soft, hard, and then you are talking about the fold structures and all that. Okay. Let us move ahead. Okay. So, another example, Ramganga diversion tunnel in Himalaya was excavated through poorly cemented sandstone, which became more soft due to when it came into interaction with water. Okay. Seepage problems resulted into the roof collapse. Okay. This is another one, Umyam Barapani tunnel in Meghalaya also faced similar problem when it was excavated through a softer rocks. Okay. And this is we have commonly observed that limestone, okay, because mostly the basic composition is the calcium carbonates, and it will react with water, and because of the dissolution activity you may face problems of caving subsurface. Okay. The surface you will see, okay, fine, it is good, but subsurface there will be dissolution activities and formation of cavities will be there. So, you are having hollow portion at the base, okay, and you are having a structure on the top, it will result into the formation of the sinkholes and it will collapse. Okay. So, this is another problems in terms of the limestone. Okay. Again, limestone is a sedimentary rock. Metamorphic rocks, if you look at gneiss mainly, okay, which are similar to granites in terms of their hardness or durability. Okay. So, they are hence can withstand the tunneling process without lining. Okay. So, if you are coming across gneiss, is good. Okay. Also, the gneiss structures facilitate excavation because they will be having some sort of an structures which are seen in the typical rocks. Okay. So, that will allow you to excavate things faster as compared to if you are coming across granites and all that. Okay. Schist phyllites are highly foliated structures. So, we in the previous part we talked about the foliated and non-foliated rocks in the metamorphic part. Okay. So, you please refer that. So, schist and phyllites are foliated and soft, easy to excavate, but will need proper lining. Okay. So, again there will be a problem in that. Quartzites are massive rocks, okay. They are very hard and difficult to excavate and need no lining. Then marble again as a part where you metamorphose limestone, you will get marble. So, virtual are compact and has granular structure. So, this will be good in terms of that. Okay. But the presence of calcite, okay, which is having the hardness 3 with excellent cleavage facilitate excavation. However, they are susceptible to the erosion. Okay. So, if you are having like similar to limestone, you are having will be having high erosion if you are having marble. Okay. But in terms of the compactness and they are good. Okay. Slates again, when we are looking at the sedimentary rocks, we are having shales, and here we are having slates. Okay, metamorphosed rock. Now, shales are rather soft and with typical slaty cleavage. Okay, needs lining. So, if you come across slates, you will have to go for lining. Okay. Now, location of tunnels, if we look at very quickly. So, we are having an folded structure. So, the sketch shows your anticline and syncline here. Okay. And then there are two tunnels which are been given here, like tunnel A and tunnel B. Okay. Now, tunnel A has been taken up across the core, or it is traveling along the core of the anticline, and here also the B is along the core of the anticline, and the sands, the rocks which we are having like shale and grete, or we say conglomerate here. Okay. Now, the problems which will be faced here will be something like this. Okay. So, folded rocks are under great strain. Okay. So, we will see a lot of tensional cracks or the joints which are developed here, which may continue for a couple of kilometers or maybe meters and keep on like in continuing for longer distance. Okay. So, folded rocks are under great strain, and then subsurface removal of the material, okay, may cause collapse of roof or caving. So, if you are removing the material from here, of course, you are releasing the strain. This may result into the collapse of the roof and all that. Okay, because you are excavating the part which is in extreme under strain. Okay, here. So, it is always better to put tunnel along a thick limb or and parallel to the fold axis. Okay. So, you have to identify what is the fold axis, how it is, what is the strike of the fold axis and all that, and try to identify the thicker limb, the thicker bed of in the limb, and then accordingly you should put it. Okay. Now, example, if tunnel is made along the crust, okay, of the fold, where it will comprise numerous tensional fractures. Okay. Frequent rock collapse from roof may occur. and along with this you will have seepage problems also, because your fractures will facilitate seepage into that tunnel. Okay. So, which overall in the sense which will reduce the competency. Now, along the trough, this is the B part which has been shown here. Okay. If you take this one along the B part, the folded beds are highly compressed there. Okay. Not very easy to excavate again. So, tunneling work will be difficult, okay, and slow and expensive. Also, percolation of water will be very high in the trough part. So, syncline is again not advisable. So, in case of tunneling along the limb, no such problems are faced. So, if you take this example, okay, so what we is been shown here, that there is a thick limb of sandstone here, okay, and you are putting the tunnel along the thick limb. So, you are getting the same rock through and through this tunnel. Okay. No doubt the limestone is setting up, shale is setting up, but this is incompetent rock, and you are also avoiding the limestone. Okay. So, you have excavated in the sandstone part, okay, which is good. So, depending on that what type of rocks you are coming across, so you try to identify the thicker limb, and along the limb which parallel to the fold axis should be taken up for the tunnel, best portion for that. If you look at, this is the photograph which shows the rail track here, which goes through this tunnel here, okay, and this which is crossing the limb. Okay. So, this is the limb here. If you see this part here, this is the edge of the limb, this is another one. So, this is the folded structure, and this is a thicker limb. So, they have identified the one limb, and through that they are putting, okay, close up of that, and this is close to Shimla. When you go to Shimla, this is on the way actually. Okay. Now, another example, one we talked about, that if you are having a thicker limb, we put the tunnel across or along the strike of the fold axis, but another is if you come across and put the tunnel perpendicular to the fold axis, okay, which is again not advisable, because you are having different rocks which are getting folded. So, if you are having a horizontal layers like this, okay, and then when you are folding, like this is sandstone here, this is shale here, and when you fold it, okay, what you are coming across, you are having this, okay. So, you are having sandstone here, and you are having shale here. Okay. Now, if you are putting this, your tunnel, you are coming across different type of layers. Okay. You are having these shale, then you came across sandstone, then sandstone, and then shale again. Okay. So, you are coming across the different layers. Okay, we will stop here, and then we will continue in the next lecture. We will talk about the different type of like rocks and all that, and how we have to put the tunnels.